Let's now have a look at some devices aimed at enhancing mixing. Fins are projections into the duct with built-in injectors, which aim to push the point of entry of the fuel further into the airflow. Their shape and edges can be designed to induce turbulence and hence aid mixing, as already discussed. The problem being that if they are too short, then they are ineffective at obtaining fuel penetration, but if they are too long, they induce drag and its associated losses. When a fin crosses the whole duct, it's called a strut. And one particular engine design is based on struts and is known as a Scramjet. In this design, the compression surface is also built in to the crossing struts. This idea would induce good mixing and is an elegant, innovative design, but has obvious disadvantages in terms of its drag because of the area in contact with the flow. However, these have not been fully explored satisfactorily, and so this is still an interesting concept awaiting further research. On a related topic, injection from razor thin injectors crossing a duct has also not been explored completely. Pylons are a variation on fins, where a projection ahead of the injection port, in the case of the diagram shown a normal injection port, shapes the flow parameters and the flow profile to encourage maximum mixing before the flow encounters the fuel. The issues are similar to those explained for short fins. Another strategy is early injection of the fuel into the stream, often in a compression surface. This allows more time for mixing and perhaps the use of different fuels at different entry points. You could extend this idea even injecting the fuel well before the engine on, for example, a spike. Several such systems have been suggested, but the main problem is premature ignition of the fuel or fuel loss due to overspill or leakage. This situation is also complex to model because of the changes in the flow parameters. Two other less popular methods should also be mentioned before we finish this section. The first is to use projections into the duct to induce shock waves, which might aid mixing, although you might question this for the reasons we discussed earlier. Shockwave structures may also be able to ignite the fuel-air mixture and hold a flame during burning. A second method is to use resonance effects, sometimes induced by cavities within the duct, to enhance mixing. These systems have not been explored in sufficient depth yet due to the difficulties associated with simulating and testing them. Standing back for a moment and surveying all the different methods mentioned here and the various papers published about these, many claim enhancements on the basic mixing scenario outlined in the last section. However, few have proved this in practice. The quoted figures for enhancements seem to hover around a factor of 2 to 5 above the basic turbulent mixing scenario. This is still not enough to give us a usable engine. One exception to this is the Scramjet, which claims to be a complete solution. However, as we discussed earlier, this remains to be proved.